Welcome to Study Loop.
This is the answer to Chapter 17, problem number 61 from the Smith Organic Chemistry textbook. And in this problem, we were asked several questions about curcumin, which we're told is a yellow pigment isolated from turmeric. And so the first question that we're asked, so curcumin is here drawn in its enol form, and we are asked to draw the keto form and explain why the enol is unusually stable. So the keto form, nothing about the majority of the molecule is going to change. So the only change is going to be here. This will now be a carbonyl. And like I said, nothing else about the molecule. Oops, I drew that wrong. Nothing else about the molecule is really going to change. Okay, so here's the enol form, or sorry, here's the keto form, which we were asked to draw. And so there are a couple reasons why the enol form is unusually strong, or unusually stable, rather. So we get intramolecular hydrogen bonding here between the carbonyl oxygen and the hydroxy hydrogen. And then the other thing is, in the enol form, we have conjugation, a high degree of conjugation. So all through the, really all through the entire molecule. But when we draw the keto form, you can see that conjugation is broken right here. And since that's the case, it's going to be less stable. So the enol form is actually quite stable for that reason, because of the high degree of conjugation. Okay, so that's part A of this problem. Part B of this problem asks us, explain why the enol OH proton is more acidic than an alcohol OH proton. Okay, and so rather than, here, I'll go to a new page, but rather than redraw the entire molecule, I'm going to use R groups. So the whole part of the molecule that we're talking about, this is really the important part, the center. So when we deprotonate the enol oxygen, when we take its hydrogen, so it's now going to have 3 lone pairs and a negative charge. And so we can draw some resonance structures here. So these electrons can move like this. So we now have this resonance structure with the lone pair and the negative charge there on the center carbon. And then we can also move electrons like this and draw another resonance structure. So like this. Okay, and so we now have 3 lone pairs and a negative charge on this oxygen. And so it's this high degree of resonance stability a high degree of resonance stability in the conjugate base is going to correlate with a stronger acid. So that's why the enol hydrogen is more acidic than an alcohol hydrogen. Okay, so for C, it's colored because of its many conjugated pi electrons. So we learned conjugated pi electrons. So we learned that they're gonna shift absorption from the UV range to the visible range. So that's why it's got such a distinct color because of its conjugated pi electron system. And then D, why is curcumin an antioxidant? And so, as we learned in chapter 15, the requirement for an antioxidant is a phenol group. And so curcumin has two phenol groups, two phenols. And so I'll say phenol acts as antioxidant. And again, curcumin has two phenols. And so it has two parts of it that are able to act as an antioxidant and inhibit a radical oxidation pathway. Okay, and so that's the answer here. Yeah, so B, C, and D are right here. And then here's A, the keto form, and an explanation as to why the enol form is unusually stable. And that's the answer to chapter 17, problem number 61.